The slightly high pressure air moves through this pipe section. With this valve, we can control the mass flow rate or the volume flow rate that is
Sir,
going through the, yeah.
so screen is not visible.
Oh, sorry.
And you were not audible before,
You
like,
cannot see anything?
no, sir.
And
And
your
before
voice
also you
is
were
not
not audible,
audible.
sir.
Okay, sorry. Okay, maybe there is a problem with the internet connection here. Okay, no problem. We'll begin again. Okay, can you see now?
Yes, sir.
Yes, sir.
Thank you. Thank you. Okay, the objective of this particular experiment is to determine the forced convective heat transfer coefficient experimentally and then compare the forced convective heat transfer coefficient that is obtained from the empirical relations. This is the major aim of this particular experiment. Before going into the how this particular experiment can be performed, let us see the details of this particular apparatus. Here what we have is a air blower here. The objective of the air blower is to suck the atmospheric air and it discharges a slightly high pressure air and with a slightly higher velocity. And this slightly high pressure air goes through this pipe section. With the help of this valve, we can control the mass flow rate or the volume flow rate that is going through the test section. We'll see what exactly here is a test section means in the later part. So with the help of this valve, we can control the mass flow rate or the volume flow rate of the air through the test section. Here, the working fluid that we are dealing in this particular experiment is the air. Note that particular point. And this is the test section that I was talking about. With the help of the valve, we can control the mass flow rate or the volume flow rate that is flowing through this particular test section. So this is a simply a hollow tube. So this is an extension of the hollow tube. And here the outside portion of this test section is wounded with an heater so that we can give an appropriate amount of heat input. And also on top of the heater, we are insulating whatever the black color thing that you see is that is the insulation covering so that the heat transfer from the heater to the atmospheric air is minimal. Essentially, here we are trying to minimize the heat transfer loss by other modes. And the other components that are part of this experiment are here. Here we have an orifice meter here, which helps us to quantify the volume flow rate that is flowing through this uh, tube. Here, before the orifice meter as well as after the orifice meter, we have connected it to an YouTube manometer so that we can find out which in turn helps us to find out the volume flow rate. When you see the particular formula to obtain the volume flow rate through the orifice meter, then you'll realize why we require to obtain the pressure drop across the orifice. Here this is the exit of the that particular pipe. As you can see here, this is simply a hollow, and also here the manometric fluid is the water. Yeah, this is the you can see this is the hollow portion, and simply the air at a higher velocity entering the test section leaves here after it gains some heat from the tube which is heated by the heater. And now let us see a bit more details here. And here we have mounted 8 thermocouples and 6 are mounted on the test section region. And just a moment. Yeah, so 6 thermocouples are mounted axially on the test section region, and 2 other thermocouples are mounted, one at the inlet to the test section region and one at the outlet to the test section region, so that we can find out the inlet temperature of the air to the test section as well as the outlet temperature of the air at the exit of the test section. These 8 thermocouple temperatures can be read from this temperature indicator here. By rotating the knob, we can read all the temperatures from 8 thermocouples. Here again, we have a dimmer start here, which in turn helps us to control the power input to the heater. That is to control the heat input given in this particular experiment. These two are the one is for switching on the blower and one is for switching on the power supply to the heater. So essentially these are the major components in this particular experiment. What we will do as for the experimental procedure, the first thing that we will do is that we will switch on the blower and we control the this valve in such a manner that there is an appropriate amount of volume flow rate is flowing through this test section region, which we can qualitatively get from the difference in the manometric reading. After doing that one, we will switch on the power supply. By adjusting the dimmer star, we can give an appropriate amount of power input to the heater. After that, once we have given an appropriate amount of power input, the tube surface is heated and the air, which is at atmospheric air, more or less, is flowing through this portion. As the tube surface is heated, heat flows by conduction from the heater to the tube and then by convection from the tube surface to the fluid, here the air that is flowing through the test section region. Here the flow is induced by the external means. Here we are using blower to induce the fluid motion over the test through the test section region. Here the because of that one, we're calling it as a forced convection. If the fluid motion is induced by the natural currents, then that type of heat transfer mechanism is called as natural convection. We will see in the other experiment where we induce the heat transfer from a fluid which is in motion to the surface which is at a different temperature, where the fluid and surface, solid surface, both are at a different temperatures. The heat is transferred in that particular experiment is by force natural convection. In this particular experiment, here the fluid motion is induced by the external means. Here the heat is transported by the forced convection. As the this test surface is at a higher temperature because we have switched on the heater, heat transfer takes place from the air that is flowing through this test section and the tube surface that is at higher temperature. And the air leaves the test section at a higher temperature. Here we can see that the after the system reaches the steady state, that means the amount of heat input that is given when it is equal to the heat that is carried away by the forced convection, then the all the surface temperatures will not change with respect to the time. Again, similar to the previous experiment, we have to, after switching on the power, we need to take the 8 thermocouple readings for every 10 minutes. And when the consecutive set of readings do not change, then we can say that the system has reached the steady state. That means the heat input given is equal to the heat carried away by the forced convection plus the nominal heat heat losses by heat transfer to the surroundings as well as by the conduction through the other portion of the tube. When that particular state is achieved, then we will switch off the electric heater first. After some time, we'll turn off the blower. This is the experimental procedure. Now let us see how the calculations will be performed once the experiment is over. You can again please go through that video as Sir has elaborated a bit more in detail about the experiment. If at all I have missed some other details. Excuse me. So these are the specifications of the different components involved in the experiment. We know the diameter of the test section, that is 36 mm, and also we know the length of the test section also, which is covered with the black insulating material, which is 45 centimeters, and the diameter of the orifice, which will be useful in the calculation of the volume flow rate, which is equal to 1.4 cm, and these are the ranges of the blower, voltmeter, ammeter, and the temperature indicator used in the experiment. And the chromal aluminum couples are used in this particular experiment. As for the heater, this is the nichrome wire heater, which is wound around the test section. As for the procedure, just to go through it again, the blower is started and airflow rate is adjusted with the help of the valve. Here we need to select the appropriate amount of the airflow rate so that we can reasonably predict the convective heat transfer coefficient from the experiment. Then we will adjust the dimmer stat for for some voltage as well as for some current which is flowing through the electrical heater. So these details will be given to you by the TS. After doing that one, after giving some constant amount of power to the heater, then we will note down the temperature readings that are from T1 to T8. Six thermocouples are mounted on the test section region, actually at different locations, and two other thermocouples are mounted, one before the test section, one after the test section, so that we can find out the temperature of the air before it enters the test section as well as the temperature of the air after it leaves the test section. We will take these eight thermocouple readings for every 10 minutes until the two consecutive sets are equal. Once we achieve that particular state, we'll switch off the blower. After that, we'll switch off the power supply. You can see here we are giving a constant power supply. So we'll note down the current as well as the voltmeter uh, readings. This is the observation table which will be given to you by the TAs. T1, T2, T8, sorry, T3, T4, T5, T6. These are corresponds to the temperature along the test section. T7 is the inlet air temperature and T8 is the outlet air temperature. So one should remember that this inlet and outlet air temperature will be uh, significantly different whether you do the experiment in winter or whether you do the experiment in summer. So for every 10 minutes, we'll note down these readings, and after some time, the system will reach the steady state. As for the calculations, in order to find out the average surface temperature of the test section, we'll simply average the all six temperatures. This will give us the average surface temperature, and we'll find out the bulk mean temperature of the air, which is equal to the inlet temperature of the air plus outlet temperature of the air divided by 2, at which at this particular bulk mean temperature will obtain the or will obtain the properties of the air, which in turn will be used in the further calculations. So note that this is the one important point. As the temperature of the air is changing along the test section, so in order to average those effects, so at the beginning the temperature of the air will be lower. As it picks up heat from the tube surface, its temperature is gradually increased, or it is steadily increased along the length of the test section. So to have those averaging effects, we'll use the bulk mean temperature for the calculation of the properties of air. Voltage multiplied by current gives us the power input to the heater. Here, although we give this much amount of heat to the surface, not everything is transferred to the fluid that is flowing through the test section. As I have mentioned, there are some losses from the heat transfer from the heater to the insulating material, which in turn to the atmospheric air. In order to find out the actual heat that is carried by the air from the surface via forced convection, will apply a steady flow energy equation, which you might have learned in the thermodynamics, to the test section region, where you assume that the change in potential and kinetic energies are as zero and the work interaction as zero. So the total heat gained by the air is equal to mcp T8 minus T7. Here m is the mass flow rate of the air, and here Cp is the specific heat of air. In generally speaking, this Cp value should be obtained at the bulk mean temperature. Now, as I have mentioned, we are using the orifice meter here to measure, to determine the mass flow rate to the test section region. By using this particular formula, we can find out the mass flow rate through the test section region. This again is applying the Bernoulli's equation to the inlet to the orifice up to the at the area where the orifice diameter, where its diameter is minimum. So we know these two diameters, diameter of the orifice as well as the diameter of the test section. So we can find out the area, cross-sectional area. These two areas are used as A1 and A2 here. This H is the difference between the two sides of the manometer, and this is the density of the water, and this is the density of the air. These two should be taken, this rho A should be obtained at the bulk mean temperature. Again, A1 and A2 are the areas of the orifice as well as the test section. Once we know all these areas, and if we substitute them, we can find out the mass flow rate through the test section region. Once we know the mass flow rate, then we can obtain the other quantities. That is, the first one is the forced convective heat transfer coefficient from the experiments. From the Newton's law of cooling, heat transfer rate from a surface to a moving fluid is given as Q, that is, the heat transfer rate is equal to A H delta T. Here the delta T is the temperature difference between the bulk fluid temperature and the solid surface temperature. A is the surface area through which the heat transfer takes place. Based on that formula, here the surface area is the pi dl, is the perimeter of the test section, and the temperature difference is the Ts, that is the solid surface temperature, which we have obtained here by averaging all the six thermocouple temperatures, and TBm, that is the average between the inlet and outlet temperature of the air. If we substitute these all the known quantities, we can find out the actual heat transfer coefficient. This is calculated based on the actual heat input given to the heater. As I was mentioning, not everything is transferred to the fluid. Then we have also obtained the actual heat that is transferred to the fluid from the energy balance using this particular equation. Then we will substitute this Q here, that is actual heat transferred to the air, divided by the pi d1 L Ts minus Tbm. In that particular fashion, we can obtain the post-convective heat transfer coefficient experimentally. Now, let us see how one can obtain the forced convective heat transfer coefficient from empirical relations. We have, we have obtained the volume flow rate of the air through the test section, and we already know the cross-section area of the test section. By dividing the volume flow rate with the test section, you can find out the velocity of the air through the test section. Once we know the velocity, at a later stage, you will learn that the non-dimensional convective heat transfer coefficient is a function of Reynolds number and Prandtl number. Those two are also non-dimensional numbers. As for the Prandtl number, this is the property of the fluid. And we will obtain the Reynolds number for this particular experimental conditions. Reynolds number is defined as rho V d1 by mu. Rho A is the density of the air, V is the velocity, and d1 is the diameter, mu is the viscosity. Once we substitute all these quantities, we can find out the Reynolds number, and as per the Prandtl number, you can obtain also, that is the property we can obtain by referring the corresponding property tables at the bulk mean temperature. This forced convective heat transfer coefficient is sensitive, or it depends on the several parameters, that is the flow conditions. It depends on the properties of the fluid and its velocity, as well as the shape of the solid, and also if there is a phase change involved or if there is no phase change. So it is really sensitive to several parameters. For example, the correlation that we are using for this particular experiment is the following one. This correlation will be completely different if the flow is over the tube. In this particular case, we are considering that the flow through a tube. So this is an internal flow condition. If the flow is over a tube, then one has to select an appropriate correlation for the flow over a tube. Or if the flow is over a flat plate, then one has to choose an appropriate correlation for calculating the non-dimensional convective heat transfer coefficient, that is Nusselt number. Okay, based on these quantities, we can find out the Reynolds number. Prandtl number can be obtained from the property tables. And in this particular case, here the surface, solid surface is at higher temperature than the bulk fluid. The heat transfer takes place from the solid to the air. Here the air temperature is increased, so this particular constant, commonly written as N, when the fluid is being heated, it is taken as zero point 0.4, and if the fluid is being cooled, then it is taken as 0.3. And once we substitute all these quantities in this empirical relation, we can find out the Nusselt number. Nusselt number is equal to HD1 by Kf. So here K is the thermal conductivity of the fluid. In this particular case, Kf is the thermal conductivity of the air. In this particular fashion, we can calculate the forced convective heat transfer coefficient from the empirical relation. Then we can see what is the difference in the convective heat transfer coefficient that is obtained from the experiment as well as that is obtained from the empirical relations. Usually, empirical relations are commonly being used in the design of heat transfer equipment. So instead of conducting the experiments to obtain the forced convective heat transfer coefficient, will only measure the properties such as the appropriate dimensionless parameters and properties at the required temperatures, and will obtain the convective heat transfer coefficient from the correlations only. Okay, that's all for today. Please refer to the experiment, to the video that is given by the sir.
So one doubt,
Again,
sir.
yeah,
So what do we take the value of coefficient of discharge of orifice meter?
that will be given to you by the TA.
Okay, sir. Thank you.
Okay, that's all, guys. Vishnu, have you taken the attendance?
Yes, sir, I have taken attendance. I will just say the absentees. If
Yeah.
anybody is there, you just say it. Okay. Roll number 6, 15.
Yes, I'm present.
Present. Okay. Roll number 15, 18, 20, 21, 24.
No, I think 21 is here. Sharan.
Oh, not responding, sir.
Okay. It's not. I can see.
21. Yeah, it is there. Okay. 21 is present. 24, 25, 30, 38, 44, 45, 48, 53, 63, 68, 69, 76, 77, 88. Is anybody is there? Okay. Okay, other students, Ravi Kumar, you can change your name as your roll number and name, okay?
Okay. Okay, guys. That's all for today. So similar to the last week, the deadline for submitting the report for this particular experiment will be until the next week.
We have one more request. Please don't upload experiment 1 files in the experiment 2 folder. We will not take them, okay?
Okay. So,
Okay, sir.
okay, if there are, okay, that's all for this week. So we'll again meet in the next week. Okay. That's all, guys.
Thank you,
Thank
sir.
Thank you, sir.